I'm Paul Nowazinski. I'm in the emerging technologies team at DDN. I've been working there for about 2 years, I think something like that, like 22 months. I work with a couple other guys that come from HPC storage backgrounds, and I'll tell you about what we've got. I got a few introductory slides here. I'm sure most of you guys know who DDN is. This was surprising to me, though. Our main office is now in Sunnyvale. I thought it was in Chatsworth. But I work out of New York on the East Coast, so I'm kind of on my own in my little home office. But yeah, I mean, DDN has been around for a long time. One of the reasons I decided to join the company a couple of years ago was because the company was, in my eyes, had always been focused on HPC and high performance storage systems. Some of the of the few storage companies that are focusing in this area, DDN had always impressed me, which is why I decided to join from academia. Here's a smattering of DDN customer logos, varying from Department of Energy in the U.S. to numerous academic scientific institutions, to lots of institutions in business, not only in HPC but in other areas of the markets as well. So I guess DDN's been around since '98, and I think there's a pointer on here, right? Perhaps not. Obviously, the technology that I'm going to be talking about today, briefly, is on the right-hand side of this bar, 2014. It's called an infinite memory engine. But if we go back from there, we see that DDN has been supporting some of the fastest, or if not the fastest, parallel file systems in the industry, using parallel file system technologies such as Lustre and GPFS. And the presence in the top 500 is there's a lot of saturation of DDN, lots of DDN presence in the top 500. So this is telling me anyway, that in the top machines, DDN is able to provide the best value and performance for the largest systems. So sort of where I guess the funding for our projects, or my project in the Emerging Technologies group, comes from DDN's investment in storage exascale technology, which I think over the years is slated to be something like $100 million. So the technology that I'll talk about here is mainly funded through this, and what we're trying to do is something that's a little bit newer than the parallel file system technologies that are in use today. So one of the main drivers of our technology, and I'm sure you guys have seen this graph, which came out of Los Alamos from our friend Gary Greider. But basically what it's showing is that if we look at storage system performance versus cost going into exascale, if we try to use an all-disk approach, the cost becomes prohibitive. If we try to use an all non-volatile memory approach, the cost is also prohibitive. So basically what we have to do is come up with some sort of hybrid scheme which basically amounts to separating the capacity from the performance. So can we buy a smaller subset of storage elements that give us our terabytes per second of performance while using disk to get capacity for free? Is there a laser on this? Thank you. So basically we want to be here. Lower is better on this graph. And it's pretty amazing because a couple of years ago when I started on this project, it was definitely the case that NAND flash technology, the price per megabyte a second was still not very, very compelling. But now the storage system that we have in our booth is using low-cost flash technology, which is actually very, very fast. And I'll show you some more. The amount of storage bandwidth that we can fit into just 1 or 2 U's is pretty impressive. And what it's showing me is that this trend, this graph that was made, I don't know, 5 years ago or something, is coming to fruition. So this is I would say also a function of cost. But if we go with a pure hard drive solution, moving into the terabytes per second range, the number of hard drives starts to get it starts to get pretty massive. And the thing is, 3 terabytes per second, we're already going to start seeing this, probably in the next 12 months or something. So I mean, this is right on the horizon. If we think about Moore's law, when we get into this time frame, we're going to start to look at number of disks in the hundreds of thousands to get the necessary bandwidth. So I mean, it's pretty much the case that we're reaching the ceiling of reaching the top end of how many drives we can put into a system and really expect to get performance and reliability. But if we also look at the power utilization in these systems, that are totally based on hard drives, the power requirements are immense. Whereas if we use the hybrid approach, we see we get about 4x the performance with the same power consumption. So obviously there's something that needs to be honored here. This is we can provide systems with this performance with the same power utilization that we have today. So the work that we're doing is more on this problem, I would say. It's to facilitate the use of hybrid systems, flash for performance and hard drives for capacity. But this is my background personally, from problems I've been working on maybe for like the last 7 years, really focus on this idea of efficiency. And this graph comes from Argonne National Labs. They took some very detailed usage data on their parallel file system over a number of months, and they were kind enough to share this data with everybody. But what we see is that they bought 40 gigabytes a second, and if we look at their utilization over a number of months, what we see is they very almost never hit the peak. So essentially, they have a lot of bandwidth sitting on the floor that's not being used, and this plays well for this concept of burst buffer, because if we can figure out, if we can provide low-cost flash systems to deal with the peaks, even though in this graph there aren't very many of them, we can drastically lower the cost of the storage system. But what this also tells me is that the utilization efficiency is really bad, and if we're going to go through the trouble of introducing new types of storage systems that use hybrid storage, we probably have to figure out why the performance efficiency is bad today, and hopefully we can improve it in this next iteration of systems. So if we look at efficiency, why is it so bad? And it's always been pretty amazing to me, coming from the HPC background, how it's kind of like assumed that you're going to drop 60% or 70% of your hard drive performance on the floor. I mean, it really is the case. You do some simple math. I mean, even with DDN systems, which are relatively efficient, if you just add up the aggregate spindle bandwidth in your system and take that number versus the number that you're going to get through an application, it's a big difference. So if we think about why that is, there's lots of ugly reasons. And usually, what it amounts to is that there's, even though we call them parallel file systems or, RAID storage with parallel drives, there's serialization all over the place. If you think about it at the RAID or the block level, you have read-modify writes happening all the time to underlying storage. And this is happening generally because the application doesn't have the ability to present a large enough buffer to the storage system. We also have this issue of lock contention, where parallel file systems generally have to serialize certain types of workloads. Like one popular workload is when we have multiple application threads on different nodes writing into the same file. at that point, the parallel file system has to ensure that the application threads aren't modifying the same page simultaneously. To do that requires a lock on the network. So we can show workloads that are relatively common, that should get reasonable performance, but the parallel file system is getting in the way. And the problem that we face as storage system designers going into this next epoch of systems is that the number of concurrency through the number of cores is going to increase dramatically over what we have today. So what this means to storage system designers is that we're going to have many more producers or possible producers on the network that are generating IOs, and which will probably mean that in general those IOs are going to be smaller, which are going to perturb both of these situations. I would say one of the next most obvious problems with today's parallel file systems is that we have this notion of what I call the weakest link. And the weakest link is something that is caused by horizontally scaling lots and lots of parallel file system servers together, and then expecting them all to have the same performance characteristics at any one time. So when you're pushing lots of I/O through a parallel file system, you're only as fast as the slowest component. And this is a pretty general HPC problem, which is why large HPC application programmers like low latency systems and really fast networks, because everything works on the concept of a barrier. And until the last thread hits the barrier, you're not going to proceed. It's the same when these applications do I/O into the storage system. If one server has, say, a rebuilding RAID set, something, maybe there's network congestion in part of the fat tree. There could be lots of different things that are going to cause blockage. And if you think back a few slides to the Argonne case, where they're not able to saturate their storage system, it's probably this and the previous slide, which are generally things that are preventing the applications from, being able to impart their data into the storage system at full bandwidth. So if we look at performance as a function of the I/O size, and what I'm characterizing here is like non-mergeable writes. So essentially what this test is showing is that if we take one core, if we have, say, a few hundred cores on the network, and each issue an adjacent I/O, what we see is that until we get into the upper 8 megabyte I/O range, we can't really drive the parallel file system. As our I/O size comes down, our performance efficiency is much lower. And this generally is, I think, why large HPC deployments have trouble getting lots of efficiency out of the storage that they've bought. And the thing is, this doesn't matter. We can do these same experiments on disk or on NVRAM, and we see the same results. So basically, what this tells me is that the physical mechanics of the disk aren't the only factor here. These are things such as what we spoke about on the previous two slides. There are protocol inefficiencies. There's locking. There's still read modify writes that are happening, especially on SSDs, which are very costly. So what this also tells us is that moving forward, we're going to, if the applications expect to get good efficiency out of the storage system is going to force those applications to behave. Meaning that they're going to have to do all the coalescing, do all of the hard work to make sure that they're presenting large IOs into the storage system. But if we go back to the Argonne data, we know that that's just not what application programmers do. They usually find the worst thing to do this file system because it's probably the most convenient way for them to program their application. So moving forward, instead of having the storage system force these rules onto the application, we probably should have the storage system be more flexible. So the system that we've been designing is we're trying to solve some of these problems in what I think are innovative ways. And I would, you may have seen this term floating around in the last couple of years called parallel log structuring. me and one of my coworkers, we sort of come from this HPC background that pioneered these techniques, 6 or 7 years ago. And really what this allows us to do, first and foremost, is it allows the application to impart lots and lots of data into the system, sort of regardless of the I/O pattern. It's because of the way we're indexing I/Os is different than like what something like Lustre or GPFS would do. What it amounts to is that we can get more parallelism out of the I/O channels. One of the really cool things that we still really haven't begun to explore, but I know it's possible through the algorithms and protocols that we're using, is this notion of dynamic load balancing. And really what this means is that if I've got a couple slow I/O servers on the network, instead of everyone going as slow as those slowest nodes, we can actually route the right I/Os around the slow nodes. So this I feel like is going to allow us to horizontally scale better, because as we're horizontally scaling, we're not going to be subjected to 1 or 2 nodes that are slowing down the whole system. Now, one of the big problems with parallel log structuring is the fact that when you write data into the system, it's actually hard to read it back, and that's because you don't have a layout, an algorithmic layout like you would have with Ceph or Lustre or GPFS. What we have to actually do is we have to index or track each I/O as it comes into the system, and this is very expensive. So the work we've done with IME, most of the work is actually done on this data structure, which allows us to still have these benefits without the penalty of being able to do readback. So this is basically a slide which gives us a sort of graphical representation of the different features that we're aiming for in the system. Some of them are not fully implemented at this point, but we're working on it. So this is data that we measured at supercomputing in 2013. We have a demo also in our booth at ISC, which has slightly better performance, which I'll explain. But if you think back to the previous slides where I was showing the graph of the performance efficiency based on write size, what we can show here is that with the system that we've designed, we can take that the small case, this is the 4K case, which is this 125,000 concurrent 4K IOs into the system, and we can max out the storage hardware. So in this system, what we're talking about is I think it's a 50 gigabyte per second max. If we run that same workload directly to the parallel file system, because of the lock manager, we can basically bring it to its knees. So what we're able to do with this system is take workloads which are very inconvenient for the storage system and make them fast. So this is essentially a burst buffer demo that we did a few months ago, and what we're showing here is a 50 gigabyte per second peak bandwidth. I think this was for this system we use 14 1U servers, each with 7 SSDs. So it's fully commodity. It was running FDR InfiniBand. And with IME, we could do this workload is a 4K strided write into one file. So this is the same workload that would see like maybe 20 megabytes a second to a parallel file system, but doing it to IME, we can actually we can max out the hardware. So what we did here in this experiment is we showed 3 writes going at full bandwidth to the IME system in this small write strided workload. Then what we did is we migrated the last checkpoint, we migrated it out to the parallel file system. And the parallel file system here has a peak of around 4 gigabytes a second. So what we're able to do is take those essentially random fragmented IOs that came into the IME system, sync them to SSD at full bandwidth, and then we would untease them and present them to the parallel file system in a way that allowed us to max out the parallel file system. Because if we had done this workload directly to the parallel file system, we would see like 20 megabytes a second. So So the stuff that we're showing here is, we've done some work on the hardware platform. This hardware platform, it's fully commodity SSDs and, super micro servers or whatever. And we can get 10 gigabytes a second throughput to this box, which is 2U. And on the floor today, what we have is a 16U service section, I/O service section, which will yield a bandwidth of about 80 gigabytes a second. So this is, so if you guys are interested, this is what we're showing in our booth, and we could, I'd be glad to discuss more in detail, how it works or whatever. But that's it. I think I went over. I apologize. But maybe lunch is ready now.
Probably ready now. Oh.